Okay, so let's do another example from the gas mixture. So in this problem, we have a pipeline. The diameter of the pipe is given, 914 millimeter is the diameter of the pipe. And in this pipe, we have natural gas passing through the pipe at this speed. So the problem statement says that the natural gas consists of 90%, 95% of methane gas and 5% of ethane gas, and that percentage is by volume. Excuse me. The absolute pressure in the pipeline is given. Also, the temperature in the pipeline is given. The question is asking for the mass and the volumetric flow rate of the natural gas within the pipe. So let's say this is our pipe and we have natural gas passing through the pipe. The velocity of the natural gas is 3 meter per second. What we know from the gas is the temperature, which is 15 degrees C. And also we know the pressure, the absolute pressure, which is 690 kPa. And the question is asking for the mass flow rate, okay, as well as the volumetric flow rate of the gas within the pipe. So the unit of mass flow rate is kilogram per second, for instance, and the unit of volumetric flow rate can be meter cube per second. Like the question is asking how much mass is passing through a specific cross section at a given time. Let's say what is the kilogram of gas passing through these cross section during 1 second. Okay, so the problem statement tells me that the natural gas that we have has 95% of methane gas and 5% of ethane gas by volume. Okay, so what I'm going to do, I'm going to see if these two gases are behaving ideally, step one, and if so, I'm going to obtain the gas constant of the gas mixture that I have here. Okay, so let's start with this one first. What I have for methane gas, the temperature is given, so based on that, I can obtain the reduced temperature. My goal is to use the reduced temperature and the reduced pressure to obtain the Z value for each gas, for this one and this one separately. And based on the Z values, I can decide whether these gases are behaving ideally. So that's my goal. I'm trying to obtain Z value. Okay. So the reduced temperature is the temperature over the critical temperature, but when you have a ratio of temperature, you're always careful with the unit. The unit should be in Kelvin. So it's going to be 273 plus 15 Kelvin because the temperature is given at 15. And you go to table A1 and you obtain the critical temperature for this gas in table A1, and that is 191.1 Kelvin, and that gives you a reduced temperature of 105. I also calculate the reduced pressure, which is pressure divided by the critical pressure. So the pressure is given at 690 kPa. In the same table, you're able to obtain the critical pressure. Just be careful with the unit that is given in that table. Table A1 is megapascal. So if I have kPa here, I need to convert this critical pressure from table. And that gives me a ratio of 0.148. All right. Now what you do, pretty much like before, you go to table, actually figure A15, and based on that, you obtain the Z value, and that is 0.98. Okay, so let me just show you A15. I'm not really going to get the Z value from A15, but just to review how this A15 looks like. We have done it a couple of times, but just for the sake of review. So this is my A15, what we have here. On the horizontal axis, we have PR. Most likely, you cannot really read it well because it might be out of focus, but just look at your own table. PR is on the horizontal axis, and on the vertical axis, it's Z. So we are looking for Z. And what we have is bunch of constant TR lines or constant reduced temperature lines. So in A15, there are two figures, in fact, one on top and one on the bottom. So the one on top has PR range from 0 to 1, and the one in the bottom has a wider range of PR, and that starts from 0 all the way to 7. So you have it in your figure, in your tables. Go through that. You should be able to obtain this Z value. So I'm doing exactly the same thing for the other gas. So let's obtain the Z value for the other gas. The reduced temperature is temperature over the critical temperature. So once again, the temperature is the same, and that is 273 plus 15 Kelvin. But this time, the critical temperature is different. So you want to get the critical temperature for this gas from table A1. So you go to A1, and that gives me a critical temperature of, in my notes I just had the final answer. So for this gas, sorry about that, again, most likely you cannot really read because it might be out of focus. So this is the gas, ethane gas, and then the critical temperature is 305.5 Kelvin. All right, 305.5 Kelvin, and the ratio is going to be equal to 0.94. It's a dimensionless number. You do the same thing for the reduced pressure, and the critical pressure comes from the table for this particular gas, and converting to kPa, it's going to be 4480 kPa, and that ratio is 0.154. So again, you go to figure A15 and also A15 here, and you obtain the Z value. So Z is 0.94. Okay, to obtain the Z value, obviously it's not an easy job to get the Z value. So just do your best. Don't worry like about the number of decimal that you can get from the figure. Don't worry about that. Okay, so my conclusion based on these two Z values is that the components are behaving ideally. The reason that I make that conclusion is because here the Z value is almost 1, and we know that for ideal gas Z is equal to 1, and also here Z is pretty close to 1. Okay, definitely it's not exactly 1, but still pretty close. So let's say the components are behaving as an ideal gas, and we know from before that if the components are behaving as an ideal gas, then the mixture is also behaving as an ideal gas. So that means in this schematic here, the natural gas at this condition is behaving as an ideal gas at this temperature and this pressure. All right, so what I'm going to do, I'm going to treat the natural gas as an ideal gas here. So we know that in ideal gas, the mole fraction is basically the number of moles of each component over the number of moles of the mixture. So this is the mole fraction. Ni is the number of mole in each component, and Nm is the number of mole in the mixture. But speaking of an ideal gas, that ratio is the same as the volume of each component over the volume of the mixture, or volume fraction basically. Okay, so just be careful that this is the characteristic of the ideal gas. So we discussed about that in a previous video. So if you go to your notes, this is where we were discussing about that. So we said for an ideal gas mixture, the mole fraction, which is Yi, the pressure fraction, which is Pi, and the volume fraction, which is Vi, of a component are identical. So this is exactly what I'm doing here. Yi is equal to the volume fraction. and yi itself is the mole fraction. Okay, so before that, before jumping into here, I should have made a conclusion that each component is behaving as an ideal gas. Therefore, the mixture, which is basically natural gas, is also behaving as an ideal gas. Okay, so I know that the mole fraction for the methane gas is equal to 0.95. Okay, so the reason that I wrote this down is because I know that the mole fraction for an ideal gas is the same as the volume fraction. And in the problem statement, it says that the volume fraction for methane is 95% or 0.95. So this basically comes from the problem statement. The same thing for ethane gas. That is 0.05. That is my mole fraction for the second gas. Okay, what I'm going to do, I am going to obtain the gas constant for the mixture, Rm, based on the equation that we have, which is Ru, the universal gas constant, over the apparent molar gas. Okay, so once again, this Rm is gas constant of the mixture. Ru is the universal gas constant, and mm is apparent molar mass. By saying apparent molar mass, I mean this is the molar mass of the mixture. So molar mass of the mixture. Okay, so if I want to find this Rm, I need to have mm, because Ru is a fixed number. Okay, Ru value wise is 8.314 kilojoule per kilomole Kelvin. I mentioned a couple of times that you can easily obtain this value from table A1, so you do not really need to memorize that. But the point is, Ru is a constant number, no matter what gas you're working with. But here, I need to find mm. But obtaining that mm is pretty simple, right? The way that I'm going to obtain mm is this way. So mm is equal to sum of mole fraction of each component multiplied by molar mass of that component. So I have two components. Let's start with this one, 0.05 multiplied by molar mass of this component, which is 30.07 kilogram per kilomole. And I will explain after that what these numbers are, plus 0.95 multiplied by 16.04 kilogram per kilomole. Okay, so let me clarify what these numbers are. So this portion is for my ethane gas, and this portion is for my methane gas. Okay, you know what this number is? This is the mole fraction of ethane gas. This number is the molar mass for ethane. Molar mass for ethane. And where the question is, where do I get it? Where it comes from? It comes from table A1. Same thing here. So this number is the mole fraction for methane gas, and this number is molar mass for methane gas, which comes from table A1. So same thing here, A1. Now you know what these terms are. So this part is for one component and this part is for another component. So if you do the math, you will be able to obtain mm apparent molar mass. And value-wise, that is 16.74 kilogram per kilomole. Okay, now that I have this mm, I'm gonna plug that into this equation and solve for rm, because this is what I'm looking for. I'm doing all this calculation to come up with this rm. Okay, if I have rm, then technically I can solve the rest of the problem. So I'm gonna use this to find rm. Rm is going to be equal to, so let's say this is the equation I'm using, 8.314 kilojoule per kilomole Kelvin over mm, 16.74 kilogram per kilomole, and my rm is going to be 0.496 kilojoule per kilogram Kelvin. So this is my rm. Now the point is, why am I looking for rm? The reason that I need to have the rm value is for the next step, I'm gonna use the ideal gas law, which is PV equal to RT, okay? Pressure, specific volume, gas constant, and temperature. I'm applying the ideal gas law for the mixture, so that means my pressure is the pressure of the mixture, the specific volume of the mixture, or the gas constant of the mixture, which by the way is exactly right here, and temperature of the mixture. Now look at this equation. The pressure of the mixture, I have it. The problem statement gives me that. If I go back to the problem statement, where is it? Here it says, so this pressure is the pressure of the mixture. So PM is checked. RM, I just found RM. This is checked. Tm is also given in the problem statement. So based on that, I can find the specific volume of the mixture. And if I have the specific volume, if I have the velocity, I'm able to obtain the properties that the question is asking for. So the pressure is 690 kPa. Specific volume of mixture is equal to Rm, which is 0.496 kilojoule per kilogram Kelvin, multiplied by the temperature of the mixture, which is 15 plus 273 Kelvin. Be careful that in equations like this, your temperature should be in Kelvin. So that gives me the specific volume for the mixture equal to 0.207 meter cube per kilogram. By the way, I'm gonna make a video talking about this equation. I'm guessing that maybe like you have definitely you have seen different forms of these. All of them are kind of the same. I'm gonna walk you through the different format of this equation. So if you are kind of confused about these, don't worry, I'll put a video and you see how this thing works. Sometimes I have Rm here, sometimes I have Ru on the right hand side, sometimes I have N as in Nancy on the right hand side, sometimes I have Z. So you may be confused with all different type of equation. I'm gonna list all of them in one video and I'll discuss about that. So this is my specific volume for the mixture. Okay, if I go back to the problem statement was asking for the mass flow rate m dot and the volumetric flow rate v dot. Okay, but I can easily use this specific volume to obtain those properties. So m dot, or mass flow rate, is equal to the volumetric flow rate AV over a specific volume. This is cross-section area of the pipe, this is the velocity of the flow, and this is the specific volume of the mixture. So specific volume with the unit in meter cube per kilogram. This V is the velocity, meter per second, and this A is the area of the pipe, which is meter squared. Okay, so if you work with the units, you will see that you are ending up with kilogram per second. All right, so area of the pipe, so I have a pipe here. The diameter is given, so I know what the diameter is. This diameter is equal to 0.914 meter. So based on that, I can calculate the area of the pipe. It's a circle, so it's gonna be pi over 4 diameter squared. That is my area. Velocity is given 3 meter per second, and specific volume I just found that in the previous page, that is 0.207 meter cube per kilogram. You do the math and you will and you will end up with 9.5 kilogram per second for the mass flow rate. So here the mass flow rate of the natural gas is 9.5 kilogram per second. That means in one cross section of the pipe, let's say here, in this cross section, during each 1 second, 9.5 kilogram of the natural gas is passing through. Okay. Also, I want to find the volumetric flow rate, which is exactly the denominator of this equation. So the volumetric flow rate, whatever you show that, Q is equal to AV. So by saying Q, I mean volumetric flow rate with the unit in meter cube per kilogram. So that is area pi over 4 diameter squared multiplied by the velocity, which is pretty much like what we had here. And that is equal to 1.96 meter cube per second, or let's say Q, or volumetric flow rate, is 1.96 meter cube per second. Or if you want to convert it into liter per second, it will be 1960 liter per second passing through that cross section of the pipe. So these two are the answer to the problem.